This is an explanation of a lot of the different relationships between chords and secants and tangents and their lengths when they intersect inside and outside a circle, and also arc measures. So just to get started with this one, which you probably have seen before, if you have this central angle here, ADC, that's the same measure as this intercepted arc, arc ABC, whereas the inscribed angle, because its vertex E is on the circle, is exactly half of the central angle, half of the arc. Also over here, this angle formed by a tangent and a secant, so this angle here will be half of this arc. So even though this is outside the circle, this tangent, it's still, you can still consider it an inscribed angle, the vertex here being on the circle. So this inscribed angle, half of the red arc, this inscribed angle, half of the blue arc. Okay, now if you have two chords intersecting inside a circle, then this angle here, and of course these two are vertical, so they're congruent, these angles will be the average of these two arcs. That is, you add the blue and the red and you divide by 2. So you see that if we add up arc AFE, we add up arc DGC, divide by 2, we get this angle ABE. So these match up, and we can move these around. You'll see that they numbers change, but they remain the same as each other. So if they intersect inside the circle, you add and divide by 2 to get angle measure. Now, intersecting outside of a circle, two secants intersecting outside of a circle, you don't add and divide by 2 for these arcs that are formed. You subtract and divide by 2. So you take the big arc, the one farther away from this intersection point, minus the small arc, the one closer, divide by 2 to get this angle. So big arc minus small arc divided by 2 is the angle. Same thing for tangent secant. Big arc minus small arc divided by 2 is the angle. Occasionally you'll be given different information. Maybe you're given this arc down here, you've got to subtract from 360 to do something with these arcs. But the idea is the same. If it's outside the circle, big arc minus small arc divided by 2 is the angle. Same thing for tangent, tangent. Big arc minus small arc divided by 2 is the angle. Now for this situation though, there are no extra pieces as there were here and here, these extra pieces, or over here we have an extra piece. For tangent, tangent, it's just the big arc minus the small arc. And you also know these two add up to 360, so that's another relationship. So that's arc measures as we have intersections inside and outside the circle. Now we look at lengths of segments. So if we have two chords intersecting inside the circle, the product of the opposite pieces are equal. So here green times orange is going to equal blue times red. So I can move this thing around, and these individual lengths changed. Move this around. These individual lengths changed. However, the product of the opposite pieces, so blue times red, green times orange, will be the same. So that's inside the circle, the products are the same. Now for secant, secant, the way this works is the outside piece times the entire thing is equal to the outside piece times the entire thing. So it's not outside, inside, outside, inside. No, it's outside times the entire length. So GD times GA is going to equal GF times GC. Same idea for tangent segment. Outside times the entire thing is outside times the entire thing. Of course, for a tangent segment, the outside is the entire thing. So you can say outside times the entire thing is just outside squared, because outside is the entire thing. And this eventually can go all the way back to tangent segments, which we've already discussed, where you could say outside times the whole thing, outside times the whole thing, but then they're just equal to each other. So some sample problems. Okay, so this is back to arc measures and angle measures. Intersecting inside the circle, so you add them and divide by 2, and you get 87 degrees. So that's inside the circle, you add them. This is a situation, it's outside the circle, so subtract big minus small divided by 2, that's 70 divided by 2 is 35 degrees for x. Same situation here. Big minus small divided by 2, that's 90 over 2, 45 degrees. Now this situation may not seem like enough information, but you know if this is x, then this arc over here must be 360 minus x, because these have to add to 360. So big arc, 360 minus x, minus little arc, x, divided by 2 is equal to 60. Big arc minus little arc divided by 2 is the angle. So the top becomes 360 minus 2x divided by 2 is 60. I'm going to multiply both sides by 2, so I get 360 minus 2x is 120. I'll add 2x, but I'll also subtract 120. So when I subtract 120, I get 240. Add 2x, I get 2x. So therefore, x is equal to 120 degrees. And then here we have 140, and therefore this arc over here must be 360 minus 140 minus x, because we got our 140, we have our x, so this is whatever's left. So this ends up being 220 minus x. Okay, so now we can say big arc 220 minus x minus little arc x divided by 2 is equal to the angle 38 degrees. So big arc minus little arc divided by 2 is the angle. It's minus because it's outside the triangle, not inside. So we get 220 minus 2x over 2 is 38. This time I'll divide everything by 2 over here. So 110 minus x is 38. Subtract 38, and I get, let's see, I get 72 and add x, so x is equal to 72 degrees. So that was dealing with arc measures. And let's see, one more with an arc measure type problem. Okay, because this is an inscribed angle on a diameter, it's a diameter because it goes through the center. I know this is a right angle, so that's 90. Let's see, I can also, if I wanted to, what else? I can draw down here, and that's also going to be a radius, so that'll be the same length. So this will be 60 because it's equilateral, and if this is 60 and this is 90, that means x is going to be 30. Okay. Now, what else? I know that we have tangents, and this is a radius, so right angle and right angle. And this is, if this is 60 in here, this angle must be 120. So now I've got 120 plus 90 plus 90 plus y is equal to 360. I get that by looking at this quadrilateral. And so if I subtract the 90, the 90, and the 120, I get y is 60 degrees. Okay, now we're on to looking at segment lengths, not arc and angle measure. So chords intersecting inside a circle. So to do that, it's 2 times x, so 2x is equal to, it's opposite pieces, 8 times 2.5. And 8 times 2.5, so okay, so 2x, 8 times 2.5 is going to be 20, so x is equal to 10. For this one, it's they intersect outside, so you do outside 5 times the entire thing, 5 plus 10 is 15, is equal to outside, which is 4, times the entire thing, which is 4 plus x. You've got to add those two pieces, so you get 75 is equal to 16 plus 4x. Subtract 16 and we'll get 59 is equal to 4x. So x is 59 divided by 4, or 14.75. Okay, over here number 15. For this one we do outside times the whole thing. So outside times the whole thing, 2 plus 9 is 11, is equal to the outside squared because it is a tangent segment. So we get y squared is 22, so y is rad 22, whatever that may be. Okay, for this one, let's see. All right, the radius is 12, so that means that this is going to be 12 as well. And so, all right, and that means the entire diameter will be 24, okay. So what we can do is say, we can say 8 times 10, all right, we have 8 times 10 is equal to this piece, which is x, times this other piece. And if the whole thing's 24 and this is x, this piece in here must be 24 minus x. So 24 minus x times x. So you get 80 is equal to 24x minus x squared. And we can rewrite that as x squared minus 24x plus 80 is equal to 0. and we'll try factoring. So two numbers that multiply to positive 80 and add to negative 24. So let's see. So we got minus 4 minus 20. So x is either equal to 4 or 20. Well, 4 plus 20 is 24, so that's the whole thing. But clearly x is the smaller piece, and so we're going to go x equals 4. And then this problem over here, again, with intersecting outside the circle, it's outside 4 times the whole thing, 12, equals outside z times the whole thing, z plus 12. And you see we get a quadratic equation here. So 48 is equal to z squared plus 12z. Subtract the 48 minus 48. And may have to use the quadratic formula, but we'll try to factor. Two numbers that multiply to negative 48 and add to 12. Let's see, I can't think of anything that's going to work, and so what I would have to resort to is the quadratic equation. So z is negative 12, it's negative b plus or minus b squared is 144, minus 4 times a is 1, because there's 1z squared, and then c is negative 48, all divided by 2 times 1. Now, what will happen is if you choose the negative answer, you'll get something that's just not going to work geometrically, so we would get rid of the negative answer and just leave it as plus, and this was negative 12. So negative 12 plus is plus, and then 4 and 48, or 4 times 48, it's 192, and so 192 and 144, let's see, 192, 144, so this ends up being, let's see, 336 all over 2. Now, you're going to need a calculator at some point, so this is probably when you'd want to pull that out. This one I'm not going to solve the algebra, but I will set it up just to show that outside times the whole thing is equal to outside times the whole thing, which in this case is 7 plus y plus 3. And you distribute, it's a quadratic equation. Actually, this one wouldn't be quadratic. Let's go ahead and do this one. 64 plus 8y is equal to, this becomes y plus 10. So that's going to be 7y plus 70. And I'll subtract 7y from both sides. I'll subtract 64, and I get y is equal to 6. So just to recap, for segment length, for the lengths, if it's inside, opposite products. So green times orange equals blue times red. If it is on the outside, outside times the whole thing, outside times the whole thing, outside whole thing, outside whole thing, outside whole thing, outside is the whole thing. Whereas if it's arc and angle measures, if it's inside, you add them, divide by 2. Whereas if it's on the outside, you subtract them, divide by 2. Subtract, divide by 2.